Okay, in this video we're going to be looking at box plots, also known as box and whisker diagrams, and this is essentially a visual graphical way of displaying these quartiles and to sort of give a visual representation of how the variability of the data sits across the whole range. So essentially what a box plot does is it divides all the data into those quartiles, and we need to have the minimum value, the lower quartile, so we need 5 numbers to do a box plot, the median, our upper quartile, and the maximum score. Now, written like this, if we just put it in brackets, written like this, it's not actually in the textbook, but this is referred to as a 5-figure summary of a set of data. So you may get asked to do, given a data set, calculate the 5-figure summary, so that's each of these 5 numbers. And so, as you can imagine, this is the smallest value. Our first 25% of data is between here and here, and next from 25% up to 50, between here and here, 50 to 75, and then 75 up to our highest score. So when we draw these, I like to do a regular scale, so whatever the data is, make sure this is regular, and essentially the box bit is between Q1 and Q3, and we have the whiskers coming out as the minimum and maximum. So a box plot looks something like that. I haven't assigned any values, but it is important that we map these ends and that line to values on the scale. So once we calculate these things, the scale is what we're measuring it on, and essentially this end is the minimum, this end of the box is Q1, that's the median, that line in the middle, that's Q3, and that's the maximum. Sometimes the median could actually be the same as one of these quartiles, in which case you would draw a box without a line in the middle, and you would note that here median and Q3 are both in the same place. But essentially for now we'll just stick with the standard one. So like I said, this divides the data into quarters. Here's our lowest quarter of data, our second quarter, third quarter, fourth quarter. It gives us an idea of how spread out the data is. So sometimes the box can be really narrow. Sometimes the whiskers on the end, as they call it, can be longer or shorter, and it gives us some idea of how spread out or how narrow and close together all the data is. I think the best way to get the hang of these is just to go through the motions and do quite a few. It's sort of important to try and get the scale right. At the bottom of page 28 it does say that you can just draw the box and then write the values for the various things. But what I've found in the past when students do that is they just draw a generic box they write the values on, but the shape and spread of the box doesn't give very much of an indication as to the spread of the data. So it really depends on where these values sit as to how squashed up or spread out the data is going to be. So let's have a look at the first example, and we'll just jump straight in and try and get some of these done. I might just leave that for the time being. So V 3.3, refer back to the previous example on the tree girth on page 22. So I'm just going to quickly flip back and write down these numbers. So that was this one here on page 22. Our minimum value for the tree girth was 81 centimetres. Our Q1 was 91 centimetres. Our median was 95 centimetres. Our Q3 was 99.5 centimetres. And our maximum value was 104. So there's nothing, these are just numbers that we've previously worked out. We've added on the smallest and largest, and then with these values we can then draw the box diagram. So I'm going to try and use a ruler. So we need to go from 81 to 104. How are we going to do that? Let's call that 80. I'm marking off 80, 4, let's call that 90, 1, 2, 3, 4, that would be 100. And that's 110. So I've broken these up into quarters, so that would be 85, 95, 105. So we're not going to need that bit. Okay, so essentially all we have to do is put vertical lines at each of these locations, and then we construct our box around it. So let's say if that's 80, 81 is about there, 91 is about there on our scale, 95 is exact, oops, let's line it up better, 91, 99.5 is pretty close to 100, and then 104, let's put it there. Okay, so all I've got is 5 lines. What I'm going to do is these middle ones we'll make the box out of. Use a ruler to make them nice. And then these 2 ends we will put in whiskers at the end. So, and essentially between, let's just write these on, Q1, Q3, median, max. So between Q1 and Q3, because this is the 25% mark and this is the 75% mark, in our box, that's half of our data. So half the data sits in that space. There's the median. So from this, I suppose the shape of it, about the spread of the data, because this tail is longer, probably that's the bottom half, the bottom quarter is bigger than the middle 50%, and the top little section is much smaller. So I suppose we could say that there's greater variability in the smaller tree girth, and as we go to further bigger and bigger trees, there is less and less data, or less and less trees with larger tree girth. Okay, so the next little section is how do we identify extreme values in a box plot? And this long line here is a bit of a clue. Sometimes because the extreme values are going to be at the ends, sometimes we can have lots of clustered data with a really, really long tail on one of the ends, and that will be a bit of an indication that perhaps we have an extreme value. So this is also labelled V3.3. So we'll just keep going. So if you have discovered an extreme value in your data set, it can be included in a box plot by indicating, so this is, so say we have our box plot, and we've identified that maybe the minimum value or the maximum value is an extreme value, then as far as the end of the whisker, what we would do is, if there was a minimum extreme value, we'd put a little cross on our scale to indicate that there is a bit of data down here, but we've identified it as an extreme value, so we're sort of excluding it from our box plot. So this would be the second smallest value. I think that's probably the best way to say it. So in the last video we looked at identifying extreme values. So sometimes it will become obvious if you draw the box plot and you've got, for example, I'll do one up here. This is all fairly regular looking, and then suddenly you've got something that looks like that. And that would maybe indicate that this value is extreme, because if we took that out, the box would probably stop there, but we'd still have to indicate that there was a piece of data up there. Okay, so we've got an example. The stem plot below gives data showing the time taken for factory workers to assemble electronic components. Prepare a box plot of the data. Okay, here we are. We've got the times taken by employees in a factory to assemble an electronic component. And first we need to find the minimum, the lower quartile, the median, upper quartile, and max. Let's change colour. So the easy ones, 43. And the max, 88. So for the median, we need to know how many bits of data we've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 26 bits of data. Let's just do a little calculation. Half of 27 is 1/13.5. So between 13 and 14, 13 and 14. So the median is there, which is the average of 57 and 58. So that is going to be 57.5. So these are all minutes, by the way. And then because the median was in between two bits of data, it means we don't need to exclude anything. So the lower quartile, we now have 13 bits of data in the lower half, 13 in the upper half. 13 plus 1 is 14, divided by 2 is 7. So our lower quartile is going to be the 7th bit of data. 1, 2, 3, 4, 5, 6, 7. So that's 51. And 7 from here, 1, 2, 3, 4, 5, 6, 7, 61. So there we go, we found the 5 numbers that we need to do our box plot. The next part, so that's part A. B is find the interquartile range. So remember that is just Q3 subtract Q1 equals 61, take away 51, so that's 10. C. Confirm that there is an extreme value in the set. And I'm already looking. I think that is going to be extreme because all the rest of our data is up here. And we've got one bit that's right up here. So I think that's what we're going to find. So let's just check at the bottom end first. So we want, so this is at the lower end. So we want Q1 take away 1.5 times our interquartile range. So what have we got? 51. Let's draw that meter. 51 take away 1.5 times 10 is 15. So that will be 36. And our lowest value is 43, so anything less than 36 would be an extreme value. So we've got no problems at the lower end. At the upper end, we're hoping that this one is going to be extreme. So we've got Q3 plus 1.5 times the interquartile range, which is 61. Plus 15, and that is 76. And because we've got 66 here, and then we've got 88. So because this is bigger than 76, this is an extreme value. So when we draw our box plot, which we're about to do next, we will we'll consider this as our maximum, but we'll put a little cross on the scale to indicate that this was also a value. Right, so what I will do is I'm going to rub out this bit. I'll leave those numbers because we need those for our scale, and we'll just leave that there so we don't forget. So our range goes from 43 to 88. So let's say we call that 40, 50, 60, 70, 80. That's a bit of a measly scale. 60, 7, 80. We've got to keep going. So I might just click a little bit of space there. Right, so again, all we're going to do is, so for our secondary max, what was it, 60, let's just look at the data again, 66. Okay, so we're just going to put vertical lines on our scale for these values. Don't forget to include that one as a little cross. And then we'll draw the box plot. So 43, if that's 45, must be about there. 51, it's probably best to rule these. 57.5 is going to be right there. 61, let's say it's there. And our max at 66, so that's going to be the end of our whisker, but we also want to indicate that we had a value up there. So join the middle ones. And there's our box plot, but with this representing our extreme value that we had. Because if we ended this whisker here, this whole section would have been longer than the rest of the data simply because of this one score.